Hello, good morning, good afternoon, good evening again. We are going to introduce lesson 2 on sustainable design in buildings or building science. This is the table of contents of the lesson. So we are going to speak about the heat and power, the energy and power. Those are the two main concepts that you have to learn at the end of this course. So if at the end of this course you know what energy and power is, and how to explain that, I would be happy. So this is the most important thing in this course. Today we are going to introduce the concepts, but we will speak about these concepts in every single lesson. Then we have to know the heat transfer mechanisms, so we can move the energy, or we can move the heat from one place to another, and we need to know that because we are going to do that in buildings. And finally, I will introduce the Fourier's law of heat conduction. What is this? This is physics. So this course is about building physics, so we are going to talk about physics today. First, we need to know what we are talking about. So we are talking about buildings and we are talking about energy. So when it comes to energy, there are two laws of thermodynamics that we need to know. This is common sense. These truths are self-evident, but we need to internalize what that means. So the first law of thermodynamics, it's conservation. It's about conservation. So the energy can be changed from one form to another, but it cannot be created or destroyed. Okay? We cannot say, let there be energy, ping, and energy appears. No, we can't do that. We can transform energy. So we have energy in nature, and we can make the most of that energy to heat up or cool down our buildings. But we can't create energy from scratch. We have to use natural resources to move that energy from wherever it is to our building. Or we have to remove that energy from our building to the outside. But we can't create energy. Important. The second law of thermodynamics, it's something that it's common sense again. The heat moves from high temperature regions to low temperature regions. Yeah, we all know that. We have something hot, we have something cold, so the heat moves from the hot surface to the cold surface. Again, that's common sense. But look at this, never the reverse, unless or without additional energy from an external source. Well, that's very important because human beings before us, they figured out how to work with the reverse of this second law of thermodynamics. We can now transfer heat from cold regions to hot regions. How can we do that? Well, we need devices, and those devices run on electricity. So by using electricity, which is another form of energy, we can transfer heat from somewhere that it's cold to somewhere that it's hot. It's like magic. But this is we need additional energy. So we need basically we need electricity. It might seem complicated, but it's not. Well, it is complicated, but at the end you will get to know that. Energy is what makes change. It makes change happen, and can be transferred from one object to another. So this is what we're going to study here. We are going to study how to transfer energy from one object or from one place to another. And there's something very important. We need to become familiar with units. We need to understand what energy is and what power is. And we need to understand the units of international units, and we need to understand the units of imperial units. Okay, so this is confusing, and I don't know, I wish everybody use the international units because they are common sense. The international unit system comes from France. Maybe it's one of the few things that French people have done right. But it's about dividing everything into tenths. Okay, so we have 1 unit, and this unit, 10 units, makes another different unit, and 10 times 10 makes a different unit, and everything is about 1/10 or 10 times something. This is the good thing of international units. And then we have the imperial units. Imperial units, I mean, the United Kingdom, in Scotland, England, Wales, and Ireland, they used different units. Why? I don't know why. Probably because they want to be different from the continent. And they ended up using imperial units. Those are units that come from the Roman Empire. Yeah, in the Roman Empire they used feet and yards, and yards, I don't know, I'm not sure. Anyway, they didn't change to the international system, they didn't change to the decimal system, and now everything is a mess. In the United States, you are familiar with the imperial units, but when it comes to electricity, you use international units. So that's why we need to change from international to imperial units. It's not my fault. I wish there were only one unit around the world, but there are at least these 2 units. And in different countries, if you work in some countries, you have to use imperial. If you work in other countries, you have to use international. And sometimes working in the United States, you will have to use either imperial or international. So that's why we have to become familiar with both units. And this is it. The international unit for energy is the BTU, the British Thermal Unit. And the international unit for energy, it's the joule. That J stands for joule. Joule, it's a 19th century scientist. He studied energy and energy transmission. So this unit is named after this guy, Mr. Joule. And we have another unit that it's better. So when we are talking about energy in international system, we talk about kilowatt hours. This thing, kilowatt hours. Why do we talk about kilowatt hours instead of joules? Well, because if you look at your electricity bill or your energy bill, if you are living in your own house, or if you will receive monthly, on a monthly basis, you will receive a bill, and then you will have $500 or $50 or $200, and that is related to the energy consumption. So the energy consumption can be either in British thermal units or in kilowatt hours. Usually in the United States, we receive an energy bill in BTUs if we are using gas, and we receive a bill in kilowatt hours if we are using electricity. If we are using both, we will receive 2 different bills, one of them in BTUs and another one in kilowatt hours. But BTUs and kilowatt hours are units for energy. Then we have power. Power is a different concept. Power is the rate at which energy is transferred. It's the rate at which energy is transferred. So we have the energy, and then we have the rate at which this energy is moving. And this is the power. What are the units? When we are talking about this rate, it's time. Okay, so we have the energy and we have time. So energy divided by time is power. So that's why the imperial unit for power is BTU, energy divided by hours, which is time. It's always energy divided by time. And in the international units, we have the watt. Okay, watt, it's another unit named after James Watt, which is the, if I recall, it's the inventor of the steam or vapor steam machine. Okay, another 19th century scientist, and he developed this machine, which is the basic element or the basic device for the Industrial Revolution that took place in Europe at the end of the 18th century or the beginning of the 19th century. Well, so he deserved to have a unit named after him. So this is I don't know if this is the first time you hear about these concepts. If it's not, it's a good time to refresh the concepts. If this is the first time, don't worry, because next lesson I will talk about these concepts again. And at the end of this course, you have to move from energy to power, from BTUs to kilowatt hours, or from BTU hours to watts. Okay, so this is the most important thing. And next year, if you are taking ARCH 370 building systems, the first week will be about refreshing these concepts. So you will have to show me that you remember these units. 99.9% of students don't remember that, but anyway, I still hope that some year that will happen. Okay, so heat transfer. So we have heat transfer mechanisms. So we have conduction, convection, and radiation. We're going to explain what these mechanisms are, and then we will apply these to a house or a building. So what is conduction? Conduction happens when we have a solid matter. So we talk about conduction with solids, not gases, or it's a solid. We have a matter, solid, a brick, concrete, wood, whatever, something that is solid. So it transmits or it transfers heat from one point to another point of the solid. Look at this picture. So here we have the first solid at this temperature, this solid at that temperature. So if we put these two solids together here, the heat is transferred from the hot one to the cold one, and at the end both solids have the same temperature. So that happens by means of conduction, and conduction means that we need a solid. Without a solid, conduction can't happen. Okay, so but do we have solids in buildings? Yeah, our building envelope, the walls, the windows, they are solid elements. So conduction happens in buildings. We have two different temperatures. We have a solid between these two different temperatures. So heat goes from the hot source to the cold source. The second mechanism is convection. So we need a fluid. With solids, convection doesn't happen. We need a fluid. What is a fluid? It can be either liquid or a gas. And why do we need a fluid? Because convection means that if we have a heat source here, we have a pot and it's full of water. So we are heating up this part of the fluid. And then the fluid, the molecules or the particles of this fluid can move freely in circles like this. That doesn't happen in solids. In solids, atoms and molecules are fixed in the space. In liquids, it doesn't happen. So the heat we need energy to heat up this part of the fluid, and then some molecules that are hot or warmer, they move upwards. We all know that heat moves upwards. Okay, so this is what happens in fluids, and this is what happens with convection. So do we have fluids in our buildings? We do have water. We have air. The air we are breathing is a gas. Okay, so the gas is a fluid. So if we have a heat source somewhere in our room, we heat up the gas molecules around this heat source, and then the gas moves throughout the room. Okay, so convection happens in buildings or in rooms. Finally, we have radiation. Well, with radiation, we don't need matter, so we can transmit heat by radiation through the space. The most important element in our lives, it's the sun. So the sun, it's a fireball in the middle of the universe, and we are a tiny particle again in the middle of the universe. But between the Earth and the sun, there are, I don't know, 100 billion miles or something like that. And what we have between the sun and the earth? We have the atmosphere. That the atmosphere, it's nothing. It's nothing in terms of the universe. And we have a vacuum. We don't have anything. And the heat radiation, the sun radiation, or the solar radiation, goes from the sun to the earth. Okay, so we to transmit heat through radiation, we don't need material. We can transmit radiation through the space, the void or vacuum. We can transmit radiation through elements. We have a gas, we have the air. The atmosphere is made of air, and the solar radiation goes through the atmosphere. So we can feel that the solar radiation can go through the air. We have solid elements that are able to transmit radiation, like glass. So we have glass windows, and the sun enters the building. So the glass, it's a solid element which is transparent to solar radiation. A brick is not transparent, concrete is not transparent, wood is not. But glasses or some plastics are solid elements transparent to radiation. Okay, so do we have glass in buildings? We do. So we have radiation in our buildings. Through the windows, we have radiations. Well, now I'm going to try to explain this by drawing. Okay, there you go. So let's start drawing. So the sky is blue. The grass is green. There you go. And now we are going to design a building, something outstanding. So we are creating the indoor space, like that. And yeah, this is the space. And now what do we need? We need the envelope. So we need to, if we have a building, we need something, we need a limit between, or material, between the indoor and the outdoor. So this is it. Okay, so what is, we are talking about energy, so the most important element in the building envelope is the thermal insulation. So usually we have this hatch to show that this is a thermal insulation. Okay, so and even the yellow, it's a good color to convey others that we are working with the thermal insulation. So you will look at a lot of technical drawings in which the thermal insulation is yellowish, and you have this hatch like this for the thermal insulation. What else do we have? At least we need something, a finish, internal finish. Can be wood, or can be plasterboard, or gypsum board, whatever. But we need something that is, we have this internal finish on the floor, the ceiling, and the walls. And then we have external finishes. Again, can be wood. In the roof, we would have tiles. Outdoors, on the walls, we can have, I don't know, wood or vinyl or whatever. And what do we have inside the building? We have people. So our goal is to make people feel comfort. Okay, so there will be some people there, and people are doing something in buildings. So they can be sitting down, or they can be practicing sports. I don't know, there are different kinds of peoples and there are different kinds of activities. So when we are performing an activity within the building, what do? We sweat. We sweat, usually. So we are increasing the relative humidity of the indoor air. So what do we have to do? We have to provide this guy with comfort. In winter, it's not easy because in winter in New England it's too cold, so we can have 0 Fahrenheit, and the indoor temperature, the comfort indoor temperature can be 70 Fahrenheit. So what happens? Imagine that indoors we have 70 Fahrenheit, outdoors we have 0 Fahrenheit. So through the envelope, by conduction, we will lose heat. Okay, so we are losing heat through the roof, we are losing heat through the walls, and even through the floor. And this is the formula for heat transfer. So we have U, we will explain what the U value is. A, it's the area, and 70 minus 0, it's indoor minus outdoor temperature. Okay? So this is something that we have to understand. We lose heat by conduction in winter. What else do we have? Well, this guy was sweating, and we need fresh air within the building. You can see the arrows. No, yeah, okay. So we need fresh air. The problem is that this fresh air is at outdoor temperature, in this case 0 Fahrenheit. So it's very cold. So that fresh air, we have to get rid of it once this fresh air has been exhausted. So, and this is something that we have to keep on doing continuously. So we have ventilation loads. Okay, so at least we need this. We have thermal loads through the envelope, and we have ventilation loads. So this is what happens in winter. Okay, so on this slide we are explaining the same thing. We have the house, we have a wall, so we have conduction through the wall. We have convection, because the air is moving, so you saw in my drawing that the air is moving, and we have radiation, especially if we have windows, the sun can enter the building, the solar radiation can enter the building. Okay, so in a building or in a space, we have the three mechanisms, so we need to get to know all these mechanisms, because we have to keep comfort, we have to keep this human being in comfort conditions, and the two main parameters to assess the comfort conditions are temperature and relative humidity. Now we are going to explain, this is physics, so we have seen some architecture, and now we are going to learn some physics here. We are going to study this is the Fourier's law. This guy we have here is Fourier, a French guy, and he wrote a very important book in 1822, 200 years ago. He wrote this book, La Théorie analytique de la chaleur. No, I don't know French, but something like that. And well, this is the analytic theory of heat. And he came up with this formula. I mean, this is a treatise, so there will be like 600 or 1,000 pages, I don't know. But if I want to summarize this book in a formula, this is the formula. So this is something that we all should know. If we are people studying major in the college, we all should know what this means. So this is the heat flow. Okay, so what are the parameters that affect the heat flow? So heat flow, Q, equals this K, which is the thermal conductivity, times the temperature gradient. The temperature gradient, gradient is a vector, and the temperature is not a vector. The temperature gradient is a vector. I'm not going to explain that, but that means that we have a direction. So it's not, the heat doesn't go, no, we have a direction, and the direction is from the hot source to the cold source. Okay, so that is what gradient means. Okay, so at the end of this book in 1822, he came up with this idea, and it's true. So it hasn't been changed since then. The heat flow depends on two things. Depends on the thermal conductivity, depends on the material, and depends on the difference of temperature between one part of this material and another part of this material. So it's very simple. It's very intuitive, and it's almost self-evident. So we can say, yes, sure, if I have a material here, the heat flow or the velocity or the time that the heat takes from going from this point to that point, it depends on two things. It depends on the material and it depends on the difference of temperature. If we have a very high temperature difference, the heat flow is very fast. If we have a material, for example, if I have a steel, the heat flow is faster than if we have wood. Okay, so there are two things: the temperature difference, and the material itself. And the material has this property, the thermal conductivity. Each material has a thermal conductivity. Of course, it can be much more complicated, and we can express this simple equation as a differential equation. We are not going to do that, but we have 3 dimensions, and we can complicate this. We are architects, so we are not here to complicate things. We are here to understand how things happen, and then we can apply simple formulas, not these differential equations, to study this in our buildings. Of course, we are making mistakes, but we are affecting only the second decimal. So second decimal for architects is not relevant. Maybe in other majors, they would say, what are you doing? Well, okay. In our major, the second decimal is not relevant. Even the first decimal is not relevant. Okay, so what does it mean? At the end, after developing this differential equation, we have to remember this equation here. So we have the heat flow. We are talking about conduction. We are talking about conduction because we are studying the building envelope. Then we will have to study convection and radiation because it will affect the indoor temperature of our building. But if we are designing the building envelope, if we are designing the walls, the roof, the floors, the windows, usually the first thing we study or the first mechanism we study is conduction. So we have to memorize, or not memorize, but we have to understand this formula. So here, this is the heat flow. So this is what we have to calculate, the heat flow. And it depends on this K, it's the thermal conductivity. As I told you before, each material has a different thermal conductivity. We don't have to memorize 1,000 materials because there are, we have internet now and we can access the thermal conductivity of every material in the world. So this is not an issue. And then we have the A stands for area, the surface area. So we have, this is the surface area of this element, A. And L stands for the thickness of the element. So look at this. This is a wall. So the L is the thickness, this dimension here, and A is the area of the wall. Okay, if we know the material, it's up to us. So we are architects, so we decide the materials we are working with. And then we have dimensions. We are architects and we decide dimensions of walls, roofs, and floors, and we decide the thickness. Okay? So all this depends on architects, on our design. And finally, we have a difference of temperature, so we have T1 and T2. This is winter, usually T2 is lower than T1, but if this is summer, this can be outdoors and it can be indoors. But there is always a difference of temperature. Okay, do we know the difference of temperature? We do, because indoors, comfort temperature is always around 70 Fahrenheit, and the outdoor temperature, we know that, because we have statistics or we have thermometers, so we can go out and say, okay, now it's 0 Fahrenheit or 20 Fahrenheit or 90 Fahrenheit. So we know both. We know outdoor temperature and we know indoor temperature. We know the material we're working with, we know the areas, and we know the thickness of the material. So if we know that, we know the heat flow. And if we know the heat flow, we can dimension the heating loads. And by if I know the heating loads, I can know what my electricity bill or my energy bill will be next month. So that's why this is important. Okay, thank you and see you.